So thank you very much, everyone, for attending this spatial ML seminar. My name is George Constantinidis. I'm professor in electrical and electronic engineering at Imperial College in London. And I have great pleasure in welcoming Yuzong Chen to give the March version of the spatial ML seminar. Yuzong is a second-year PhD student. He's advised by Mohammed Abdul Fattah at Cornell University. And before that, he worked on novel processing in-memory architectures for deep learning acceleration. Recently, he's started to look at efficient hardware architectures for sparse and mixed precision deep neural networks. He's a finalist of the Qualcomm Innovation Fellowship, QIF, 2024. So welcome, Yuzong. I'm really looking forward to hearing about your research.
Thank you, George, for the introduction. So hi, everyone. So today I'm going to discuss about efficient computing memory architectures for FPGA-based deep learning acceleration. So this is a joint work with my colleague, Jordan Dozo, also at Cornell, and my advisor, Mohammed Abdel Fattah. So just a few background. So yeah, these are slightly out of date, but we know that deep neural networks are everywhere. So we see this kind of image, I think, more than 5 years ago. So we know that we use convolutional neural networks for image classification and object detection, and in almost all kinds of state-of-the-art computer vision tasks. And regarding language processing, so we have a lot of like smart assistants in our smartphones and maybe iPad. So we have Apple Siri, like Google Assistant in our Google devices, and also Samsung Bixby in our Samsung devices. So now like we have ChatGPT and large language models, and hopefully they can be embedded in these smart assistants for edge devices, but currently deploying them is still a challenge. So yeah, because why like deploying DNNs are a big challenge? So there are two reasons. So first, like DNNs are very data intensive. So the model size of a deep neural network can vary from like 100 megabytes in early convolutional neural network to sometimes even 100 gigabytes to the biggest large language model nowadays, like Llama more than 100 billion. And the second reason is that because they are very big, so they are also very compute intensive. And because they involve a lot of matrix operations to do just one single inference or do just one token generation. So one inference can take order of like giga operations, or sometimes even like a tera operations for just one inference. So this is very expensive. So the two challenges actually like will raise something called von Neumann bottleneck for DNN computation in conventional hardware architectures. So as shown in the left figure, this is a von Neumann architecture in a conventional CPU. So we have this arithmetic logic unit, ALU, and memory unit, and this control unit. So basically, von Neumann bottleneck states that our system delay and power will be dominated by memory access rather than actual computation. So for most of the time and energy in your computation, you're actually spending time and energy transferring data between ALU and memory. So this is a big bottleneck. So as shown in the right figure, you can see that like this is in, I think, 40 nanometer technology node. So you can see that if you want to just do a 32 bits integer addition, it will take less than 1 nanosecond to finish this operation. But when you want to do a register data move and cache data move, it will take 2 cycles sometimes. So provided that you have a cache hit, if you don't have a cache miss, then you have 2 nanoseconds. But if you have a cache miss, then that's very bad. You have to go to fetch the data from like another memory level, usually in DRAM. So this can easily take like 50 nanoseconds, or sometimes like more than 100 nanoseconds to fetch the data from DRAM to your cache, then to your ALU for computation. So in terms of energy, it becomes worse. So a 32 bits integer add will only take 0.1 picojoule, but a cache data move can easily take like 10 picojoule. And when you go to DRAM to access just the 64 bits for a 64 bits data bus in DDR3 or DDR4, it can easily take more than 1 nanojar to just get the data from off chip to your on chip. So this is like not what we want, especially in deep neural networks. So what people are currently doing is that they always try to add more memory to the chip. So instead of relying off chip memory, so we know that like maybe NVIDIA GPU has like tens of gigabytes memory now, like inside the GPU. So we don't need to go outside the GPU to fetch the data, which will be very expensive. But the challenge is that the memory scaling is much slower compared to the normal CMOS technology scaling. So to solve this challenge, so people have proposed a new architecture or emerging technology called computing in memory, SIM architectures. So the key idea of SIM is that instead of fetching the data from memory to ALU, can we separately do some like special operation or do some important arithmetic operations just inside the memory? So in this case, we don't need to fetch the data from memory to ALU, or we can just fetch like very few data from memory to ALU to do some computation that memory cannot carry out. So for example, in this case, we can use the memory to do some like a ternary content addressable search. So this is a very conventional, I think, type of computing in memory. Although like a ternary content addressable memory has a special name called TCAM, which you guys may be familiar if you are in the circuitry area. But like TCAM, I believe is kind of special computing in memory operation because you just do a search or parallel search inside the memory without like getting the data out from the memory to ALU, then do a like a logic comparison. And you can also use memory to do some very simple Boolean logic, like AND operation or operation. But like the most important thing for us is that we can use memory to do some dot product operation, which is a fundamental operation in DNN computation. So the benefits of computing in memory is that it can achieve very low latency and superior energy efficiency because we reduce the data access from memory. So, sorry, excuse me. So basically, computing in memory, summarizing in one sentence, it reduces memory access by performing in-situ computation within the memory block. And simultaneously, so just now we talked about, I think, the second challenge, because DNN has a lot of computation. You need to like repetitively fetch the data from memory to ALU to do this massive computation. But how about the size? So DNN is very large. So can we actually do some compression, DNN model compression at the algorithm level before we do the inference in hardware? So actually, this is a very popular research area called DNN quantization. So the principle is that DNNs can be actually quantized to lower precision instead of FP16 or FP32. So this quantization can offer a very good trade-off between accuracy and hardware cost. So when we reduce the data bit width by 2 times, so you can refer to the left figure from NVIDIA. So if you reduce the data width by 2 times, you can achieve half of the addition, delay, and power because your operand bit width is reduced by 2 times. And you can also achieve 1/4 of multiplier, delay, and power because of the quadratic complexity of multiplication. Simultaneously, you can reduce the memory area and power by half. So yeah, this brings us that so our like most of us are doing FPGA, I believe. So FPGA is actually very good at low precision computing. So what we want to do is that can we use FPGA to do quantized deep neural network efficiently? Yeah, because FPGA is bit programmable. So instead of using FP16, which is not well supported in FPGA, can we use like int8 or integer 4, or maybe integer 5, integer 6 bits, depending on your algorithm. So in addition to DNN quantization, just now I also mentioned computing in memory to solve the von-Neumann bottleneck. So can we apply computing in memory to FPGA to achieve the best of both worlds? So this computing in memory can efficiently solve the problem of the massive computation and the massive data transfer between ALU and memory. And simultaneously, FPGA is very good at like low precision computing. So can we employ computing in memory to FPGA to achieve the best of both worlds? But before diving into FPGA-based computing in memory, I want to give you an overview about like a conventional application-specific integrated circuits-based computing in memory. So these two areas are kind of different, and I will highlight why they are different later. So for ASIC-based computing in memory, when we want to do a dot product, so let's first consider a matrix vector multiplication. So we have a matrix size m by n, vector size n by 1, so we get an output vector m by 1. So what we need to do is that we need to store the matrix to the memory. So assume that we have enough memory in just one memory array. So the memory array size is n by m. And in this case, so every memory cell will store a conductance. So this is called GIJ. So it will store the DN weight matrix in analog conductance, or sometimes in digital format, but storing in analog conductance is more common for like a massive parallelism, because you can, like a DN computation can tolerate some error. So even though you do this in analog domain, so you can still achieve good results sometimes, yeah, for most cases. So in addition to storing the weight matrix, so the input vector will be converted to analog voltage by a digital to analog converter. And then every voltage is a VI is applied to one row of the memory. So as shown here. So then in the next step, so every memory cell will produce an analog current. So because along this one column, you will have a Kirchhoff's law actually. If you refer to Kirchhoff's, I think, current law, you will get the sum of the current along every column equal to the dot product, or equal to like the sum of this multiplication results. So as shown in this equation. And then finally, this analog current will be converted to the digital partial sum using an analog to digital converter. So like there are several challenges in this ASIC-based computing in memory technology. So the first challenge is that the overall hardware area and energy cost are usually dominated by this expensive digital to analog conversion. So if you are familiar with circuits design, you know that both DAC and ADC, they are very, very area hungry and power hungry. So just designing one single ADC is already very difficult. But when we do memory, because memory cell is very small actually. So when you want to put some ADC here, you have to meet the area constraint. So for example, in the real layout of the chip, so the size of this ADC cannot be too big. Otherwise, like maybe you have this area for the memory cell, and then you have this huge big area for ADC. So the area overhead will be too much in that case. Yeah, so there are some research directions for this ASIC-based computing memory, and there's some actual relationship between this part and later my FPGA-based computing memory parts. But let's just first get familiar with this, how people do ASIC-based computing memory in the academia. So first, like the first direction is that we can use different types of memory technology to store the weight matrix. So different memory technologies have different trade-off in terms of speed and area and density. So we can also like use different memory technology to design a different memory cell structure. So for example, we can have more transistor in a memory cell to do like different CMOS logic operation. So this will offer a trade-off between area, robustness, and functionality. And then another direction is that so some people, they are designing very efficient analog digital conversion techniques. So in this case, we can reduce the area overhead. And for example, we can design ADC, DAC with lower noise so that we have better accuracy. Yeah. And so the last part is that so many people, they are in the architecture area. So they are designing efficient computing in memory data flow. So for example, we can rely on bit serial or bit parallel computation. And we can use output stationary or weight stationary data flow. And they can also design efficient data flow for sparse and mixed precision DNS. So for example, like if I find that like when I do structured pruning for the deep neural network, if my whole memory column is 0, then perhaps I can just remove this column and I can shift the rest of the column to the left so that I can reduce my memory footprint. Yeah, so now I'm going to talk about some basic FPGA architecture knowledge to get you familiar with how we can do computing in memory in existing FPGA architectures. So first, so commercial FPGAs, they basically contain three critical blocks, like as shown here. So the first block is called logic block. So it contains lookup tables that can implement arbitrary Boolean logic functions. And the lookup table has some inputs, usually 4 to 6. So you can do arbitrary 4 inputs or 16 inputs Boolean logic functions. So the second block is called digital signal processing units. So it is used to implement very high precision multipliers. So the precision is usually 25 bits or 18 bits. I think in Intel FPGA, the DSP precision is usually 18 bits, and in Xilinx, it can be 25 or 27 bits. And this is because that the lookup table is very inefficient in implementing high precision multipliers. So that's why FPGA just add this functionality to, like, it's kind of hard multiplier to do efficient multiplication. So the last part, this is very important, is your on-chip memory called block random access memory or BRAM. So it can give you a lot of like on-chip bandwidth to achieve like a significant data reuse and reduce the energy cost so that you don't need to fetch the data repetitively from off-chip DRAM. So because we talk about BRAM, so BRAM is the only, but maybe you can say like in Xilinx FPGA, we also have something called UltraRAM, URAM. But I mean, like the overall architecture is the same to BRAM. It's just that they have a bigger memory. Yeah, so let's first talk about the overview of BRAM, because we are going to use actually BRAM to do computing in memory in FPGA. And this is the only memory block that currently we are working on. So first, let's look at the Intel's FPGA BRAM. So it's called M20K. I think you can refer to it as a memory. This 20K means the capacity. So because it can store 128 by 160 bits like data inside this memory block. So this should be 20 kilobits. Yeah, if you do a math calculation. So how is this like data stored in this BRAM? So basically, this BRAM is implemented using a true dual port BRAM cell. So this is the cell structure. So this is like, we call this a 8 transistor SRAM memory cell. So because it has, if you count 8 transistors. And why do we call it true dual port? Because it has 2 memory ports. And you can access them from this, we call this word line, WL, and bit line. So this blue and red ports are 2 separate ports. So it means that you can use these 2 ports to do 2 read operations, or 2 write operations, or 1 read and 1 write operation simultaneously. So this is called true dual port SRAM. And it's used to implement a lot of important data structures in our accelerators, such as double buffer and FIFO. Yeah. So keep in mind that here we also have a 4-to-1 column mux. So it means that after reading out this 160 column data from the BRAM array, we will have a 4-to-1 column mux to select only 40 bits of them. So this 4-to-1 mux basically gives you your output memory bandwidth. So you can only access 40 bits data at a time instead of 160 bits. So there are some design challenges for FPGA-based computing in memory if we want to use BRAM to do SIM. So the first challenge is that since FPGA, like we compute in digital domain, like FPGA may have some analog components, but when you do real logic operation, it's always in digital domain. So the first challenge is that when we do FPGA-based computing in memory, we should avoid expensive analog digital conversion. Otherwise, you can tell the vendor that, okay, maybe you help me add an analog to digital converter inside the BRAM. The FPGA vendor will most likely say, no, we don't want to do that. Other applications will not use this ADC. It's very it's very inefficient and very power hungry and consumes a lot of the area. So the second challenge is that because FPGA is a commercial product, so when we do computing in memory, we should neither change the existing BRAM interface nor affect the existing BRAM functionality. because many people, they are using FPGA to do different applications. We can now say, okay, after adding this computing in memory technique for deep neural network acceleration, like when I buy a FPGA, okay, I can only use this VRAM for computing in memory. Like maybe I need to sacrifice my functionality as a double buffer, then that is usually not favorable. Like FPGA winners will say no. But I mean, given that the current market size of deep neural network is so big, like perhaps we can see some in the future that so people will have a dedicated FPGA architecture just for deep neural network inference. But currently, no. So the third challenge is that FPGA VRAM has limited I/O ports. So this is limited by the routing architecture of the FPGA. So because on the commercial FPGA, the routing area will usually dominate for more than 50% of the FPGA chip area. So that's why like FPGA VRAM only gives you like 40 output bits at the same time instead of 160 bits. So this is to reduce the routing congestion and also like just to reduce. Also, it can also like already satisfy a lot of application requirements. So when we add computing in memory, we should try to reuse this available ports as much as possible instead of adding extra ports. Otherwise, the area overhead will become very large. So to solve this above challenges, so we propose a new architecture called BRAMAC. So it's called Compute in VRAM Architectures for Multiply Accumulate on FPGA. So the baseline architecture of our BRAMAC is still Intel's M20K, but you can easily change this to Xilinx VRAM. It's very similar. So the data flow is that we assume weight stationary data flow. It means that we store the weight inside this VRAM, and we will stream our activation, the deep neural network activation from outside the VRAM, maybe from another VRAM block on the FPGA. So when we add this computing in memory functionality, the first thing we need to do is that how do we distinguish between computing in memory operation and conventional memory access? So instead of just using this memory block as a SIM, so we can also use it as a memory block. So we need to do normal memory read and write. So how do we distinguish between the like memory read, write, and the computing in memory? So what we do is that we can use a special configuration SRAM cell. This is very small. Like you use a lot of this configuration SRAM cells for your like routing. So this SRAM will store the mode of your memory. So you can mention that, okay, I'm using this VRAM as a computing memory block. So we will also design an embedded finance state machine in this VRAM to control our in-memory computing data flow. And then, so during the memory mode, we just set the mode SRAM to 0. And during computation mode, on same mode, we make it 1. And during this mode, we will have another constraint, but it turns out that this is enough. So when we have this VRAM configured as a computing memory block, we will only allow it to operate as a simple dual-port memory. So because in DNN, we usually just use this VRAM for storing the weight data, and we will support double buffering. So when we configure the VRAM as a double buffer, we have to make it a simple dual port because we need to read and write simultaneously. So this is a constraint, and we will say that we use this port A for write and port B for read. Yeah, we have port A and port B here. So because in this case, like we use port B only for the read operation, like this write enable signal of port B is actually idle. So this was originally used if you use port B as a write port, but now we don't use this signal because port B is a read port. So we will say that like if this write enable B is 1, so because it's actually don't care originally, but now we say that we can reuse it to signal some computing in memory operation. So if this W enable B is equal to 1, then we'll say that this address A and data A, so from port A, they will be treated as a computing in memory instruction to trigger our like computing in VRAM operations. Yeah. So then like after we trigger the computing in memory operation, So we will first send out like 32 bits weight from the main DRAM array, like which is specified by this address A, and then we will send this 32 bits weight to 4 DRAM processing elements here. So they are called BPE. So we will use this DRAM processing elements to do multiply accumulate operation for deep neural network. And then to stream in the input activation, we will use the data A port of the original DRAM interface. So these are original DRAM allowed data for conventional DRAM architecture. So we will use data A to stream in our input activation, and then this data A will go through this embedded finite state machine, and finally it will be fed to this DRAM processing elements to carry out multiply accumulate. So you can see that just now when I talk about like a computing memory, actually I didn't touch this port B. So I only use port A to get data, gets the weight, and gets the like input activation from another block maybe. So port B is completely idle actually when I do computing in memory. So this means that we can use this port B to do some other things. Like for example, like when we do computation, we don't want to say, okay, so your DRAM can only be used by your DRAM processing elements to do computing in memory operation. So we want to say that we also want to use this weight data, and we send it outside the DRAM, and so that DSP can also access it to do some operation. So in this case, we say that this BPE, DRAM processing elements, are actually complementing other logical resources. So because like in DN, we have a lot of sharing between inputs and weights. So one weight may be shared by many inputs. So when you compute different like output windows in a convolutional neural network. So this is totally like totally like favorable, because like in this case, we can use this same data and we simultaneously feed it to BPE and DSP. So we don't need to duplicate this data. Actually, in some previous works, when they do computing in memory, they have to duplicate the data storage so that one DRAM is configured as a normal DRAM so that DSP can access it, and simultaneously another DRAM is configured as computing in memory block so that they can do some operation using the DRAM. But we can do just one, we can use just one DRAM to simultaneously feed the BPE and DSP. So now let's talk about the microarchitecture of in-DRAM processing elements. So this is actually a small memory. So why we call it computing memory? Because our BPE is actually a separate, very small, like we call it dummy memory. So each BPE has a small 7x32 DRAM array, like which are dedicated for computing, and we have 4 BPEs. So this does not affect our main DRAM array, which is separate from our BPE. So the BPE can perform two multiply accumulate operations at the same time. So we define it as W1I1 plus W2I2. So we use something called hybrid bit serial and bit parallel MAC2 data flow. So this MAC2 means 2 MAC operations. So we're streaming the input bits serially. So why do we do this? Later on, I will highlight that by doing in this way, we can achieve like better performance when you do mixed precision quantization. So first, like this, the 6th row of my dummy DRAM. So this 6th row, it will store the current MAC2 results, or you can call it partial sum. And the first to the 4th row will store a lookup table to compute the partial sum given the current input bits. So you can consider that when we stream in the inputs bit by bit, the partial sum is just like if this bit is 1, so we get W1. And if this bit is 1, we get W2. But if one of the bits are 0, so we just add 0. So it means that we can use a lookup table to represent this partial sum. So if both bits are 0, both I1I and I2I are 0, the partial sum is just 0. And if one of them is 1, then it's either W1 or W2. If both of them are 1, then the partial sum is W1 plus W2. So the first rows are used to store the partial sum lookup table. And then This inverter row is used to store a temporary inverted partial sum because when we use tooth complement representation, the input bits, MSB, most significant bits, should be negative. And then like we need to do a shift operation because when we do bit serial operation, we need to shift the partial sum based on the bit significance. Yeah, and this last row, this accumulator, it will store accumulator when you want to accumulate many Mag2 results. So that in this case, you don't need to send the partial sum like outside the VRAM to do accumulation. You can just do this accumulation inside the VRAM. So this adder, you can see a read and write port and bit parallel adder here. So it's used for like in-memory partial sum of final results accumulation. Yeah, so this is our overall BRAMAC architecture. And so it was published in 2023 FCCM conference. But later we try to extend BRAMAC to support like mixed precision computation, which is very important to maintain the accuracy of DNN while compressing the model significantly. So this is called M4 BRAM. So why it's called M4 BRAM? Because it's I think it's called mixed precision matrix multiplication. So you have 4M here. So M4 BRAM. Yeah. So to just give an overview of the mixed precision quantization. So it's proposed to allocate different precision for DNN inputs and weights. So this can provide a better trade-off compared to uniform quantization, where you just have like one single precision for both inputs and weights. So for example, in this case, I can have a precision PI for input and PW for weight. So there is some like just like sparsity, you have different degree of like granularity. So for mixed precision quantization, you can also quantize the weight matrix or input matrix from like using a different granularity. So like the precision of weight and inputs, they can actually vary across DNN layers or even within the same DNN layer. So this means that we can quantize this matrix to just like 8 bits in this case. But for the weight matrix, maybe we can like quantize the first 2 column to 8 bits and the second 3 column to 4 bits. So in this case, we call this per channel quantization. So it turns out that per layer input quantization and per channel weight quantization can provide a good trade-off between accuracy and hardware overhead. So in the extreme case, you can quantize every element of this weight matrix using different precision. But in that case, you will have very, very irregular data storage memory layouts. So you cannot do this very efficiently in a conventional memory architecture, and like your hardware cannot support that because you are doing different precision at the same time. But per channel quantization basically says that I just quantize the whole matrix column using a precision. So when I fetch the data from memory, I can, for example, I can fetch just one column of the data, and this one column of data can be processed simultaneously. So to get some speed up, so the challenge of mixed precision quantization is not just the memory compression, it's also about hardware speed up. So how can we get some speed up from mixed precision quantization? So for example, when we quantize the inputs to 5 bits instead of 8 bits, can we like improve the performance by 1.6 times? So actually we can, because I already mentioned that our BRAMAC computes the multiply accumulate operation using a hybrid bit serial and bit parallel data flow. And because the inputs are streamed in like bit serially, so actually the multiply accumulate latency is proportional to the input precision. This is the nature of bit serial computation. So it means that our BRAMAC or M4 BRAM can already support like a mixed precision input quantization and give you some hardware speed up. So how do we support variable weight precision? So the thing is that currently we support 3 different weight precision, 2 bits, 4 bits, and 8 bits. So if you want to quantize your weight to 3 bits, the challenge is that, yeah, currently we just pad it to 4 bits. So basically it doesn't support 3 bits efficiently. And actually, you can also not store like 3 bits efficiently in memory. You still need to store it as 4 bits, unless you have some like a data packing unit that will consume some extra area to when you read the data, like you want to read 32 bits data, it can only store 10 3 bits number. So 10 is not a very good number for processing because usually in computer architecture, we prefer 2 to the power of something. Yeah, but yeah, maybe we can extend that in the future work. So to support these 3 different precision, we use a configurable sign extension mux. So basically, when we read 8-bit weight vector from the main VRAM, so we can either convert it to like a 32-bit sign extended vector. So why do we convert it to 32-bit sign extended vector? This is because when we use the memory to do accumulation, we have to ensure the numerical correctness. So when we add an 8-bit number to a 32-bit number, we have to first extend this 8-bit number to 32 bits so that we can add this to the accumulator. Otherwise, we will get incorrect results. So basically, this sign extension mux will say that it can convert a 8-bit number to a 32-bit number, or it can convert 2 4-bit number to 2 16-bit number, or like in the last case, 4 2-bit number to 4 8-bit number. So you can see like here, like across here means the connection. So in this case, you can see that this 8 bits are connected to different parts of this crossbar. But this turns out to be like not area hungry, because if you look at, I think in the worst case, you just need to select from 3 different inputs. In this case, you look at this column, you're selecting B1, B3 here, and B7. So you are only selecting one of the 3 inputs, and you give it to the 7th bit of your output 32 bits vector. So this max input, number of inputs in the max is just a 3 in the worst case. So this is not a very big crossbar. Yeah. So after talking about this, how we can do the mixed precision quantization in M4BM, so let's show some evaluation methodology and results. So how do we evaluate? So first we use a coffee. So this is a FPGA circuit modeling tool from Professor Von Bass group at University of Toronto. I think it's very good. You can try it out. So basically, it allows you to model different circuits in a SPICE netlist, and it will automatically size your circuits, size the transistor size of your circuits, and give you a good trade-off between area and delay. So we use coffee to model BRAMAC and M4BM circuits. Then we evaluate some like DN benchmarks on the baseline FPGAs, Stratix 10. And then when we do DN mixed precision quantization, we obtain the pre-trained model from PyTorch CV, and we conduct a fixed point quantization with a uniform symmetric quantization. So actually, this M4BM paper was published in last year's FPT conference. You can go to check the detailed evaluation methodology if you are interested. So we also use a baseline accelerator to evaluate the benefits of M4BM. So this baseline accelerator is Intel's deep learning accelerator. I think it's publicly available on Intel's website. So like in the original DLA, deep learning accelerator, so the compute unit is basically DSP. So the DSP will receive data from normal VRAM for computation. So as shown here, you have a VRAM and you send the data to DSP, then you do the calculation. And we assume with stationary data flow. So here, like we store different filters of a CNN to different VRAM block, and the same inputs will be broadcasted to this different VRAM block to give you a output feature like along different with different channels. Yeah. So how can we do computing in memory inside this accelerator? Yeah, luckily we can have this BPE inside M4BM, and this BPE, as I mentioned, it can receive data from the main VRAM array, and simultaneously this main VRAM array can send the data also to DSP because my read port is available. So in this case, we can partition the workload, the input feature, to 2 parts, one processed by DSP, one processed by BPE. And we get like different output features along the output width dimension in this case. So this is actually a heterogeneous accelerator. So because we have two processing engines, the first one is a bit parallel DSP engine. So it has just a 1 cycle latency. And the bit serial M4 DRAM engine. So the latency will be proportional to the input precision. So we actually conducted some design space exploration to find the best workload partitioning strategy so that the throughput of M4 DRAM can match the throughput of DSP because they have different computing natures. Okay, so here we show some results about speed up with input quantization. So here the width precision is fixed to 8 bits, but we vary the input precision from 8 bits to 4 bits. So every figure here, they show a different benchmark, VGG, ResNet, and the black dashed dotted line in every figure, they actually represent a 0.5% top one accuracy drop from ImageNet classification. So why do we choose 0.5%? Because it turns out to be that, so people not consider 0.5% as a negligible accuracy loss, but you can say like, okay, this can be 1%, like depending on your constraint, but we use 0.5% accuracy drop as a constraint in our work. So you can see that when we quantize the input precision to 5 bits, so in every case, so we see that we can get a like negligible accuracy loss of like a less than 0.5%. But when we go below 5 bits, sorry, like actually 6 bits, yeah, sorry. So when we quantize the input precision to lower than 6 bits, so for example, 5 bits here, so you can see that the accuracy is lower than the target. So this means that if we just rely on conventional conventional FPGA architecture, so because conventional FPGA architecture, we can rely on DSP packing to pack like multiple low precision multiplications on a single DSP. But it has some constraints, and it's showing in our paper that when you like reduce the input precision from 6 bits to 5 bits, you can improve the DSP utilization by 2 times because every DSP now can do 2 multiplications simultaneously. But if you just increase the input precision from 5 bits to 6 bits, then you cannot do 2 multiplication. You can just do 1 multiplication in 1 DSP. So if you try to increase the throughput using DSP packing, and you have to drop the input precision from 6 bits to 5 bits, but it will give you too much accuracy loss in this case. But with just a 6 bits input precision, because our M4 DRAM can still get some speed up due to the bit serial computing data flow. So we can provide like 2.16 times speed up on average over DLA. So here we have some like, yeah, I should mention at the beginning, but here this M4S means a small M4 DRAM, and this M4L means a large M4 DRAM. And we have this double pumped and synchronous. This is because in a conventional DRAM architecture, you can choose to double pump it to give you a higher throughput. Yeah, this is allowed. And after input quantization, we now switch to per channel weight quantization. So basically, what we want to do is that we quantize several channels of a filter to 8 bits because they may have a lot of quantization error. So here we show that when we just quantize 5% of the channels to 8 bits, and when we use the 6 bits input, we can get a negligible accuracy loss of like a 0.2% compared to the retrained baseline. It's actually 0.27% accuracy loss, but we can achieve 2.33 times speed up compared to like 4 bits deep learning accelerator. So it means that we just have 5% of the weight in 8 bits, but we can get a lot of speed up compared to like a pure 4-bit DLA. Yeah, then like lastly, we compare the throughput of M4 DRAM, large M4 DRAM to DSP given the same area constraint. So because DSP packing can only do like a very coarse-grained throughput improvement. So when you quantize the input from 8 bits to 6 bits, actually your DSP packing will not give you any speed up. Only after you quantize the input from 6 bits to 5 bits, the DSP packing can give you 2 times speed up. So when we have similar area budget, so the synchronous M4 DRAM can outperform DSP by 1.98 on average for different activation precision and benchmark AlexNet and ResNet. So when we use this as double pumped DRAM, so it can outperform DSP by 95 times on average. Yeah, so now I want to show the conclusion. So at the beginning, I mentioned that computing memory can offer a very good solution to reduce the cost of memory access and improve the hardware performance. This is especially important for deep neural network computation. And second, I show that FPGA is very suitable for quantized deep learning acceleration due to the bit programmable flexibility. And then based on this, we propose BRAMAC, which is a computing memory architecture based on FPGA BRAM. And then we talk about M4 BRAM, which extends BRAMAC to support mixed precision multiply accumulate computation and offer a good trade-off between accuracy and hardware performance. So then finally, we show some evaluation results. Yeah, I think that's all for my talk. And yeah, happy to take any questions. And if you have any questions about my talk, feel free to contact me through email. And feel free to check out our M4 BRAM and BRAMAC paper. So BRAMAC was published in last year's FCCM, and the M4 BRAM was published in last year's FPT.